Good. All right. Hello, everyone. Welcome to the Lab 3 help session. So Landon and I are going to go over the SR latch, breadboarding, said latch, and then the counter design. So I'm going to talk a little bit about the flip-flops, how to implement the SR latch on your breadboard, and then Landon is going to implement a counter, which I highly recommend you pay attention to, and then also watch the video later if you have any questions about the steps required to implementing a counter. Okay, well, and first, so quick overview. We've talked a lot about combinational logic using SSI components and MSI components to create to get equations and then implement those equations to do something that we want. So in class, you should have discussed for the last week or two about sequential logic. And so that is going to be kind of the bridge between combinational logic and LSI components. So things like ALUs, and then eventually we're going to make a CPU. So the sequential logic is what's going to allow us to actually compute things and kind of actually do things with our circuitry and not just have like one equation. So, right. So the first thing is an SR latch. This is a set and reset latch. I like this because it shows you the two different options. You can either do it with two NORs or two NANDs. I believe Dr. Schwartz will ask you in lab 3 to do it with one or the other, or he might just let you choose, and in which case you use either two NORs or two NANDs, but not like one NOR and one NAND. It has to be the same. And then these you can find either online or I think probably in his lectures. Yeah, and you should know how to do this for anything like a practical exam, lab quiz. You should be able to know how to create an SR latch from just 7402 or 7400 components. And then on the left and the right here, actually, we have the excitation table, I believe. So if you have a set and set is true, but reset is false, then you would get a 1 on the output. If reset is true, but set is false, then you get a 0 on the output. And then if both are true, I believe we don't know what happens because that's sort of invalid. And then if both are false, then it just continues with whatever it was set for before. All right, so this is, yes. This would be an excitation table.
What's the difference exactly?
Yeah, so a next state truth table is what you use, and where Landon's actually going to make one live in a few minutes. And that's what you use to implement a counter and to implement the sequential logic. The excitation table is, you can kind of think of it as a guide to how the flip-flop that you're working with works. So depending on what inputs to the flip-flop are true, you will get a certain output. Does that make sense?
So it's telling you how to go from output.
Yeah. So if you want the output of 1, for example, you could make S true and then R false. And that is what you would then use for your logic design. So I will talk about it in a couple slides, but sequential logic updates when you have a clock signal. In this class, we always use a rising clock edge. So when the voltage goes from 0 to, I guess, about 3.3 volts, that is when your circuit evaluates what the input is and then outputs. So if you change something in between clock cycle 1 and clock cycle 2, you might click it once and then you change it so that S is true, R is false. Click it again, your output will now all of a sudden be 1. Does that make sense? Okay. All right, and so this is the SR latch on a breadboard. So you have your axial resistors. If you bought the kit from out of the box, you have both axial resistors that you need. And then you wire those from ground to the two outer kind of connections to the single pole double throw switch, and then you run VCC to the middle one, and then you use two wires to get outputs from those. So I have another picture here, which might show it a little bit more clear, kind of on a drawing. But basically, this allows you to have one input be true or one input be high and one input be low at the same time, which is why you have two wires coming from the single pole double throw switch versus just one for the single pole single throw. Does that make sense? We can also probably send out this picture on Slack, or you can just watch the video again. When you implement it, I think it'll make a lot more sense. This is just a drawing that I had of the SR latch and the pinouts for it. So I wanted to include that. Okay. All right, I really like this picture that I found because it shows how you can use only SSI components to create the flip-flops that we're going to be using in class. So I don't know if this was shown in class, but obviously we've seen the SR latch, and this is maybe a little bit more complicated one. But the SR latch that you use, or sorry, this is an SR flip-flop. So it's more complicated because it's going to store the bit. The SR latch is what you use for the debounce switch circuit. And then you can see the JK flip-flop, the toggle flip-flop, and the delay flip-flop. So these are not things that you have to know for the lab or for the exam or anything. You only need to know the SR latch, which is what I drew in the green and blue. But I just want to show you these because something that Dr. Schwartz likes to say and reiterate is that all components are made to be scalable. So this is how we go from SSI to the MSIs of the flip-flops. All right, so with the first flip-flop, we have the delay flip-flop or D flip-flop, typically called D flip-flop, so don't really, I think it's just DFF in Quartus, so pretty short. And the way this one works is when you have a clock cycle get triggered, trigger the flip-flop, it'll take whatever the input is going in the D and just feed it to the Q. So there is an excitation table, but you can see, let me see if I can right here. So for this row here, there is no clock. So like I said, we do rising clock edge. So when it goes to the 1, it's then going to change. So you have 0 here, and this is your rising clock edge. So then once it hits the rising clock edge, it's going to go to 0. Obviously, it started at 0, so it's just going to 0 again and not changing. But then when you have 1 on the input, and the important thing, which is why I like this table for it, is when you have nothing changed, you're still at your 0, right? So if you change the input, if you have your D go true and false, nothing's going to happen until you hit that clock cycle, right? So now you've changed your input to 1, still here, and now you hit that rising edge, and now it's a 1. Does that make sense to everyone? So you would have a 0 here, for example, and then you change this to a 1, hit your rising clock edge, and now this becomes a 1, right? So it's pretty simple as far as flip-flop goes, but it's something that is very powerful that we can use in CPU design. No. Yeah. Let me show you this next one. So this one does not have the clock signal. I think this one was more of a just descriptive kind of excitation table. I liked it because it shows, it emphasizes that nothing happens until the clock gets triggered. All right. So this is a toggle flip-flop, and so it has basically two main functions, toggle or not. So as we saw in the D flip-flop, if you have any input, it'll just be passed through. In this one, you have an input that can be fed. Sorry. You have an input, and then whether or not T is true will tell you whether you flip the input or not. So obviously you can only have zeros and ones. So toggling between 0 and 1 are your only options. So starting with this line, what this line means is, let's say you have 0 coming in as your Q, and then your toggle is false. So it's not going to toggle. Therefore, you're just going to end up with 0. Same thing here. So you have this go here, and now you have 0, but your toggle is true. So you're going to have 1. So this is different than the set and reset, in that rather than having set and reset decide on an kind of asynchronous, just forcing it to be whatever you want it, you're going to have the toggle. So it's going to just still depend on the input, but then it's either going to be the same or the opposite, depending on whether toggle is true or not. All right. And then going to the next one here. Again, toggle is not true, so you end up 1 because you're just passing it. All right, and then this goes here. Toggle is true, so then you're just going to have 0 because now you're flipping it from 1 to 0. Do you have any questions about the toggle flip-flop? Now, the most complicated but most versatile flip-flop is the JK flip-flop. And the reason why this one is really helpful is because you can get a lot of don't cares, and you'll see that when you're doing your labs and you're designing your state machines, you'll see that the logic equations can become very simple for the JK flip-flop. So how this works is J is essentially your set and K is your reset. So it's similar to an SR latch, except one main thing. When they're both true, which is right here, then it becomes a toggle. So this can do, oh, actually, yeah, never mind, sorry. I didn't know if I missed something, but I didn't. So this can do pretty much everything that the last ones have done, but all in one flip-flop. So starting with if J and K are both false, you will have a hold state. So the output being fed back into the input will be the same. So if you have a 0 outputted before, and you have both of them false, then you'll get a 0. If you have a 1, they're both false, you still get a 1. And then if J is true, then you'll get a 1. Again, this is very similar to the set reset flip-flop. And then if K is true, you'll get a 0. And if they're both true, then it will toggle to whatever the opposite of the input is. All right. So that was all of them. What do we have next? Okay. Does that make sense to everyone? Does anyone have any questions about any of the flip-flops and how they work? All right. Well, Landon is going to take it away with designing a counter for you guys.
All right, so now this is like the real implementation stuff. This is the stuff you're gonna wanna pay attention to, since you'll use all the theory Joseph talked about and actually use it to create a digital circuit. So basically, this is gonna be the counter we're gonna design. You'll see it in a similar fashion to this one, where it'll start at 1, and then it'll count 5, 0, 4. So you can think of this as our sequence, and then this one is basically equivalent to restarting our sequence. So here I wrote it out in binary. So does anyone have a guess for how many flip-flops we'll need for this design? This is a trick question. 3 flip-flops? Any other guesses? 0 flip-flops? All right, well, the answer is actually 2 flip-flops. And you're probably like, wow, this actually makes no sense. We have 3 bits. But if you notice, I wrote out these numbers in binary intentionally because exactly. So if we look at the second bit or bit 1, if we classify them as bit 0, bit 1, and bit 2, you can see between all these bits, this middle bit right here will remain 0. So this is a little tricky. a little sly, but now we look at the bits on the outside, and those are the bits that are going to change. So those are the bits we're going to need to flip-flop. So off here to the left, I have 6 simple steps, and this is basically how you're going to approach every counter design in this class. So first, you'll start off with the next state truth table. Then from that next state truth table, you'll be able to create a K-map, and this from here, you'll be able to derive your like MSOP or MPOS. And remember, these two are equivalent, so you're able to use either unless explicitly told to use one versus the other. Then your next step is you're gonna actually design it, and whether that be like on your piece of paper or in Quartus. Assuming you are doing the Quartus route, you always simulate before you build because this will save you a headache. And then lastly, you'll build it and use our switch and LED circuits, or maybe even your hex to segment decoder to show that it's working. So now we're gonna do a Quartus demo, but we're first gonna start doing all 6 of these steps, starting with the next state truth table. So I'm gonna go back one slide, and we're gonna go ahead and start this so I have room to draw. All right, so with the next state truth table, basically I'm gonna go ahead and write our pattern back here at the top. So we're counting 1, 5, 0, 4, 1. So this is the pattern we're gonna be working with, and we'll make our next state truth table. So even though I said that like Q1 doesn't change, I'm gonna go ahead and put it in our truth table anyway, just so we can kind of prove this to ourselves. So first, we start with our current state. So these are all of our bits. And then I'll draw a line to separate. And then this is gonna be what we call our Q pluses. So this represents what this bit will be after our trigger. So in this class, we always use a rising edge to trigger, but of course there are other options as you get into more complex designs. So we're gonna start and do normal counting order like any other truth table. So we'll start here with 0, and then we'll count all the way up here. I'll try to do this as fast as possible. All right. So then these are all of our combinations. And now we'll reference our order up here at the top to fill this in. So basically, this first line says, when our current state is 0, what will our next state be? Anybody? Next state after 0? 4, right? So our next state will be 4 because you can see our zeros right here. 4 will always follow this. So if we want to express a 4, it's like 1, 0, 0. So this will be our next state. So now, continuing to fill out the truth table, after 1, you can see we have 5. So we'll have 1, 0, 1. And then, does anyone know what we'll have after 2? It'll be a don't care, right? Because there's never going to be a situation, unless maybe you're a faulty designer or your design messed up, that you'll have a 2 and there'll be like a following state. So for this one, we'll put don't cares. Same thing for 3. We don't have a 3 in our sequence, so we'll have don't cares. And for 4, it'll follow a 1, and then 5, after 5 will be a 0, and then there won't be a 6 or a 7. So we'll go ahead and fill these out with X's. So now we have our next state truth table, but we need an equation. So this is when we use our handy dandy tool called a K-map. So I guess before we do a K-map, we should first decide what kind of flip-flop we want. So for now, I'll do a D flip-flop just because that's the easiest. Or we'll start because that's the most intuitive starting out, I guess. So here we'll say Q2. We'll say this is our D2, this is our D1, and this is our D0. So again, this is assuming we're using 3 flip-flops. Of course, you can tell from this table that the second row, if you fill in don't cares with 0, it'll just stay 0. So we'll reflect that in our design accordingly. So first we'll go ahead and do this K-map. I'm starting off with D2. So here we'll have Q1 and Q0, and we'll put Q2 off on this left side. So 0, 1, and always when you do your K-maps, don't forget to do it in the grayscale counting order or when one bit changes at a time. So then we'll go ahead and fill it out following this column right here. So it's 1, 1, X, X, and then filling out it's 0, 0, X, X. So you can see, depending on whether or not we circle ones or zeros, it'll essentially be the same thing. So for the sake of this example, I'll just go ahead and circle the ones because that might be most students' gut reaction is to do the ones. And if you fill it out, you can see all of Q1 and Q0 change. So we can say D2 is just equal to not Q2. So this will be the equation we're feeding into the input of our D flip-flop. And we'll be able to see that design a little more clearly later. So I guess I'll make another K-map for D0. Since we know this D1 will stay 0, I'll just go ahead and skip that part and for the sake of time. So this will be 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. And then again, this will be Q1 and Q0. So now we're looking at this last column. So we have 0, 1, X, X, and we have 1, 0, X, X. And then let's say for this case, we choose to circle, let's say ones. So I'll make a circle here, and then I'll make a circle here. So of course you can try to circle zeros and do kind of the opposite, but you can see in this case, for the don't care right here, I'm choosing it to be a 1 because that benefits me. And same thing for this one. And then for these two don't cares, I'm choosing them to be a 0 to make sure we cover all of our ones. So if we go ahead and do this K-map, we'll do the circle at the top first. We see that Q2 does not change. So we'll say D0 equals Q2, and then that's negated. Q1 changes, but Q0 does not. Or with our second circle, so this is going to be Q2, and then Q0 not. Yes, okay. So perfect. So if we continue with this, now we have our equation for D2 and D0. And we've decided that for our Q1 bit, we will just tie this like to ground when we implement our design. So let's see, that's the K-map, and we have our equations now. So yeah, next is gonna be the design. So I'm gonna go ahead and try to share my screen on my laptop. Whoops. And then we'll see if we can pull up Quartus here. All right. So this is the PowerPoint. Where are we? Okay, Quartus. So I already made a project on here. So as it pulls up, you'll be able to see that. So it looks like Quartus is gonna take a minute, but you'll see I basically already designed it with our correct implementations for all our design. So once it loads, okay, so it looks like Quartus is gonna crash in the middle of this demo. This is probably pretty accurate to what you guys are seeing in the labs. Okay, perfect. Okay, lab 3 help session. All right. So this is our implementation, right? So we found D2 to be not, or yeah, D2 to be not Q2. And then of course this Q1 is going to be tied to ground. And then we got that longer equation right here that I've implemented just with gates. So does everyone kind of understand what's going on up here on the screen? So another common confusion is right here when we look at our inputs. So the qubits are actually not an input. So what we do have for inputs is our clock, naturally, so we can dictate the flipping of our flip-flops. And then we have these Q2s as an output so we can observe them. But in order to start our counts at, I believe it was 1, we use like the signal, let's say start active low. So we can use these active low presets and pre-clears to set the starting bit of our flip-flop. So for example, when start active low goes true, it clears the bit here, so Q2 goes 0, and it sets the bit here, so Q0 goes 1. So then this, since this is always 0, you have 0, 0, 1. And that'll start with the logical one we want to start with. So now I'm going to go ahead and compile this. Oh my gosh, Quartus is just causing me all sorts of pains today. Let's try to get this out of the way. All right. So we're gonna do this functional compilation. So again, this functional one is the only thing needed if you just want to simulate your design. So we'll wait for this to compile and then we should be able to check our design. So I went ahead and also made the waveform for this. So after Quartus goes through this compilation, we'll open it and check. All right, so this is our waveform. You can see start active low. I set it active low or in the true setting, so it resets our count. And then for the rest of the simulation, it's high. All right, and then we'll go ahead and do functional simulation here. Some runs. And perfect. So now here I'm expressing it in the hexadecimal radix just because it's easier to read for us. But you can see the count operates as expected. 1, 5, 0, 4, 1, and then it starts over. So it's important to note that you always have this kind of start active low because this otherwise we can't really know where the flip-flop will start. So this kind of goes into a discussion that hasn't really been covered yet in this video, which is the difference between asynchronous and synchronous inputs. So for example, asynchronous inputs will happen regardless of a clock edge, while synchronous inputs or synchronous signals depend on that rising clock edge. So you can see if I go back to this simulation and at any point, let's say I just make this 0 or true, no matter, see how I started right here, not on a clock edge or anything? When we run this, our count will immediately go to 1 because start active low is an asynchronous signal. So you can see that here. Naturally, if of course, like this count is synchronous. So when you make your annotated simulations, these clock edges are really important to show that you're moving from one state to the next. So I'll go ahead and make this high for our next simulation. Oh, this is the, all right. But does that make kind of sense to everyone? All right. So from there, I'm also going to do this same design using a T and a JK flip-flop. So we stop this share. We'll share back on the iPad so I'll be able to write. So, all right, we'll write on this. Okay. All right. So now we're going to do NSTT for the T flip-flop and then the JK flip-flop. And then we've already spent a decent amount of time, so maybe I'll skip the K map since it's a kind of a common occurrence these days. So like always, we'll start with Q2, Q1, and Q0. We'll count in counting order. Instead of just having Q2, Q1 plus, Q0 plus, and then defining those as our Ds, we'll have to use the Q2 plus, Q1 plus, Q0 plus, and then we'll also need more columns for, if I say our bit 2, or I guess in this case the third bit, is a T flip-flop, and the 0th bit is a JK flip-flop. We'll have to define it kind of something like this. So the Qs will actually stay the same from our last NSTT. So I'll just go ahead and copy those down real quick. And then these will all be don't cares. And then will also be don't cares. So now we have a couple extra steps by using these other flip-flops, but you'll see it'll greatly reduce our design in the long term. So remember when we were using D flip-flops and D2 was equal to not Q2? Well, this is basically like toggling. So we can see if we look at T2 right here, and we're looking at like this Q2 and we're comparing it to Q2 plus, you can see going from 0 to 1, that's a toggle. So that's true. And then 0 to 1 is also a toggle. And then in these don't care rows, we'll fill them in with don't cares. 1 to 0, 1 to 0, and then don't cares. So both toggles and don't cares. And then for our J0 and K0, we're going to be looking at these two rows. So this is where we get into the more complex J, K, and don't cares. So if at any point you get lost, feel free to stop me and I'll kind of go into more depth on this. So for this first row, it's 0 to 0. So like Joseph was talking about, we have two options. Since we already have 0 and we want 0, we have the option to hold, which is 0, 0, where J is 0, this is J, and this is K. This will give us our desired output, or we have the option to reset. So this would be 0 and 1. So either one of these combinations will give us our desired output. So like we did in lab 2 using don't care, we can simplify this to just saying 0 and X, or 0 and don't care. So for this row, we'll do 0x. Okay, and then moving on to the second row, we have a 1 and a 1. So again, we can choose the holds, or we can choose to set the bit, which would be this. So now you can see this first, or bit 1 changes. So you could say x0, which is what we'll write in. And then of course, this row will still be don't cares. And now let's look at 0 to 1. Well, this, we could choose to set the bit, which would be 1, 0, or we could choose to toggle it, since 0 and 1 is kind of a toggle operation, which would be 1, 1. So then this means we can choose 1x. So we'll write 1x. And then lastly, it's 1 to 0, which is basically we can choose to reset or toggle. So if you reset or toggle, then this would be x1. So you can see here off to this right side, we've gone through basically all of the combinations of our JK flip-flop. So this is something some students choose to memorize if that's what works for you. I just choose to kind of like intuit it as I work through the problem, think, oh, I can reset it or I could toggle and then do it that way. But of course, choose the method that works best for you. So then these will be don't cares. So we can do a flip-flop, or not a flip-flop, like a K-map. But since we've kind of already been talking for a while, I'll just go ahead and tell you that T2 is equal to Q2 and J0 is equal to Q2 and K0 equals Q2. And then we'll go ahead and switch back to my computer, and then I did a PDF showing this one. Share the screen. All right, and one day I'll figure out how to make this process easier, but until then. All right, so now we're gonna set this JK count as our top level. And since we've set that to our top level, we're gonna have to go ahead and recompile. But while that compiles, I'll go ahead and show you this design. So you can see, oh, I think I misspoke earlier. So T is actually equal to high, because if you go back to the NSTT, it's always 1. So that's how that works. So always toggle. And then here, JK, they were both Q2. We have our clock input driving. So it should be compiled by now. So we'll open up our simulation. And since we changed the top level, we're gonna go ahead and restore defaults. So like right here, this is the old PDF. We'll restore defaults, and now it's our new PDF. So we'll save that, and we'll go ahead and run it. Oh yeah, I'll do that as well. All right, and you can see, I believe this is the count we had, 1504. Yeah, okay. So this is the count. So you can see 2 different designs using different flip-flops, we get the same result. So let's say that some of these numbers are wrong and we need to debug. It's really hard to do it in this radix format. So in terms of debugging, I always like to do it in binary. So you just right-click this count, go to radix, and then binary. And now you're able to look at each bit individually. So let's say we know that the middle bit doesn't change. So if at any point we see a 1 in the second bit, maybe I messed up there. So I'll focus on that part of the design. So I think other than that, that's pretty much all that I wanted to cover. And then I guess since I'm sharing this screen, I'll go ahead and just do it from here. But in lab procedure, this is at the bottom of every lab doc. For this lab specifically, we're going to complete the lab quiz, and then you're going to demo your correct function for the 3-bit counter. Like always, video demos are required when you turn in your lab. And if you look at the lab doc, the appendix has some very useful information. So I guess, does anyone have any questions before we end off? Does the general format make sense on how we approach these problems? Pretty straightforward. Jasmine? Yeah, we can go over the JK. Yeah, I'll do it on my iPad. Yeah, the switching back to forth gets kind of tricky. All right. Let's see, we're gonna do. Okay, yeah. So this is the JK stuff. Do you have a specific question? Oh, okay. Yeah. So of course for the J0 and the K0, we're only looking at this 0th bit. So we'll focus specifically on this column right here and this column right here. So let me see if I can change colors or something. Like probably not. But we look at Q0 and Q0 plus. So you can see in this instance, Q0 is 0. And in this instance, Q0 plus is 0. So we're basically trying to find out what value do we need to pass in on the J0 and K0 lines such that it outputs from 0 to 0. And we find that that comes from either holding our current value or resetting to 0. Do you see why we choose hold and reset?
What is it? From the top.
So like these bits are, this first bit is J, this one's K. So the J, when this is true, it sets. So, and then when this one is true, it resets.
It's like an SR flip-flop in the sense that the J is the set,
Yeah,
K is the reset. And then this one has the added functionality of being able to toggle.
yeah. So like a SR.
So the toggle, it just like, so Q0 and, or Q plus, they're both zeros. And then toggle is one. What do we do with toggle? Like we just, since toggle is one, we just keep it as 0.
Okay, so toggle is dealing with bit 2. The toggle flip-flop is this T2 deals with Q2 and Q2 plus. Our JK flip-flop just deals with bit 0, which is Q0 and Q0 plus.
Oh,
Yes. So we basically isolate each bit to one flip-flop. So I guess for my recorder, people who are watching this after the fact, I'll go ahead and end it there. Any questions? I guess this will be on YouTube, so you can put them in the comments or put them in Slack and someone will get to them.